The law of conservation of momentum will apply to all different types of collisions. You could have 3 or 4 things colliding, and they could be colliding at angles. You could have 5 or 6 or 10 things exploding, all at weird angles in 3 dimensions. But we're going to continue to limit ourselves here to 2 dimensions and 2 objects. In this case, though we have a vector problem because the directions are not lined up with each other. We have a car of 1,200 kilograms. Let me draw this. Overhead view of the 2 cars. The bigger car, the 1,200 kilogram car, heading north towards the top of this page at 20 meters per second, and the 1,000 kilogram car heading east at 25 meters per second. They're going to crash at an intersection. So this is the before. So with all conservation of momentum problems, there's a before the event and then the after the event. And what you want to do is figure out the total momentum before and set it equal to the total momentum after. As you can see here, let's take the smaller car as our first vehicle. I'm going to call that P1 equals M1 V1, remembering that P stands for momentum. And for the bigger car, that's our second car, arbitrary, P2 equals M2 V2. Simply calculate those, and we'll do that pretty much in our head here. P1, the magnitude is the 25 times 1,000 is 25,000 units, 25,000 kilograms meters per second. And that's towards the east. Make a note of that. That's in the diagram. And P2 is 20 times 1,200, which is 24,000 kilograms meters per second towards the north. So we have to add those as vectors to get the total momentum. And I'll draw the diagram over up to the right here. If we have 25,000 units of momentum to the right and 24,000 units of momentum to the north, that's 24,000, then the total momentum, if we make our vector diagram, our resultant will be, I'll do it in blue, that's our resulting momentum. I'll call it R. But R in this case, you can use the Pythagorean theorem, 25,000 squared plus 24,000 squared, take the square root of all that, and it comes out to be 34,700 kilograms meters per second. That's the overall starting momentum. That's the important number here. That's the amount of momentum that must be conserved. We could call that P total if we wanted to. I'm calling it R here in this case. We could also figure out the angle at which we have our total momentum. We could pick that angle right there, theta. And to figure out the angle, which will be useful later on, but I'll calculate it now, tangent of theta will be 24,000 over 25,000. You can take a shortcut and just do 24 over 25 because all the zeros will cancel out. And if you plug it into your calculator, it's real close to 45 degrees because the 2 momentums were almost the same. It comes out to be 44 degrees. That's an important number. We'll come back to that. That's the angle of the total momentum. That starts with, and it must be the total momentum afterwards. All right, I'm going to go back to the after the event now. So after the event, so with all conservation of momentum problems, you have before the event happens, get the total momentum. In this case, 34,700 units of momentum at 44 degrees. You must have that same momentum afterwards. In this case, there is a nasty crash, and there's then a mangling, and this is going to be the mangling of the 2 cars here, and they're going to come together and they're going to stick together, and they're going to be a total mass of 2,200 kilograms of mangled mass. I already know that they will be traveling off in this 44 degree direction. 44 degrees. They actually they apply this law to actual crash investigation, forensic science. If somebody got killed, they have all kinds of things they look at, skid marks. I guess now in cars they have little black boxes, so to speak, like on airplanes. They have little computers in there that are keeping track of like speeds of the car and data for the car at certain times. So they actually might check that particular data if there's a real issue with a certain kind of crash when somebody got killed. but they also look at the skid marks, and they use these principles to figure out speeds and so forth to see if somebody's speeding before the crash. Anyway, these problems tend to be a little bit easier than elastic collisions. This is definitely an inelastic collision. When two things stick together, that's always an inelastic situation. There's going to be some loss of energy. We're not going to calculate that in this problem. But this one is, once again, fairly simple. I should say simpler than the first one. I'm going to call this P3 equals M3 V3. But I know that P3, the total momentum, is still this value from up above. It's still conserved. It's 34,700 units. The total mass now is 2,200 because they stick together. V3, so it's a pretty simple process here. V3 comes out to be 16 meters per second. And it's at the 44-degree angle as noted in the diagram. So this is my answer, the velocity of the mangled mass after the collision. Let me stress again, when you are doing momentum problems, conservation of momentum problems, you need to delineate the before and after the event. Here we have a gun that will shoot a bullet. The bullet is the little blue thing inside the gun here in the before picture. These tend to be the easiest kind. The explosion problems tend to be are fairly easy because the total momentum before the explosion, I'll call this P1 equals M1 V1, is 0. Okay, P1 equals 0. 0 kilograms meters per second. Nothing is moving. There's no momentum, no total momentum, no individual momentum. I also want to mention at this point that the law of conservation of momentum doesn't apply to a single object. It applies to systems. Single objects can gain or lose momentum, but the system momentum cannot change. That's what the law of conservation of momentum says. In this case, the system momentum must be maintained at 0 kilograms meters per second. In this case, the system is the gun and the bullet. Isolated, we're forgetting or ignoring that there might be a person holding the gun. A gun will recoil into the shoulder of a person if it's not being held tightly. So here we're ignoring the person, and we need to conserve the momentum. I'll call the gun momentum number 2, P2 equals M2 V2, and the bullet is P3. Once again, P is momentum. P3 equals M3 V3. And here I have to start on the far right over here. I know for the bullet, P3, I know the mass of the bullet, it's given in the problem above, it's 50 grams. Well, that's 0.050 kilograms. You have to move the decimal 3 places, times the speed, 280. So the momentum of the bullet here comes out to be 14 kilograms meters per second. So the momentum was not conserved for the bullet. It gained momentum. However, the gun has a negative momentum, it's going backwards, of the same magnitude. So therefore, and we don't need to put the negative in the equation, this 14 comes over here, and you have the momentum of the gun, 14, equals the mass of the gun, which is 4 kilograms, times V2. All right, so V2 is very simply 3.5 meters per second recoil backwards. That's our answer. That's the recoil velocity of the gun into somebody's shoulder if it's not tight against your shoulder. If the gun had been tight against somebody's shoulder, all that momentum would have been transferred to the gun and the person as the system. Even further, it would be transferred into the earth because the person would be actually standing on the earth. So the system would be the gun-man-earth system. But here we're just looking at the bullet and the gun as the system. Finally, here we have an impulse problem. And the law of conservation of momentum would apply here, but we're not going to actually apply that law. We're just going to look at impulse. When you have things that change their momentum greatly over a short period of time, we're usually talking about impulse. The other clue here is asking about impulse, but also the fact that we're looking at forces and times of application of a force. These are all clues that you're dealing with an impulse problem that we could further investigate with conservation of momentum, but we do not need to apply that principle at this moment. Now, when anything changes direction like this baseball, or anything that bounces, there's a great change in momentum. great change in velocity. Here the ball was going 40 meters per second to the right, and now it's batted back at 50 meters per second to the left. Its actual change in velocity is 90, not just 10. It's not just speeding up from 40 to 50, it's actually changing direction. So that's a total change of 90 meters per second. But we'll hold that thought for a few minutes. What we want to look at here is the initial momentum of the ball, which is pretty easy to figure out. P1 equals M1 V1. So the initial momentum of the ball is 0.960, that's the mass, times its V1, 40 meters per second. That's basically a 90 mile per hour fastball. So P1 comes out to be 38 kilograms meters per second, say to the right here. And P2 is going to be 0.096, that's a 0.960, that's the mass of the ball in kilograms, times 50. It's coming back straight at the pitcher. He better duck. But if you multiply the mass times the velocity here, the momentum of the ball coming back towards the pitcher is 48 kilograms meters per second. Once again, that's a huge change. It looks like it's going from 38 to 48, just picking up 10 units of momentum, but it's actually, like the ball, it has to stop and reverse direction. So the delta P here, the delta P is actually the 38 plus the 48, and that's only when you have something that reverses direction. If only it's speeding up in one direction, then the change, yes, would be 10. But here, technically, one of these numbers would be negative, like the 48 would be negative, and then 38 minus a negative 48 is like 38 plus 48, which is 86 units of momentum change. The delta P is 86 kilograms meters per second. That's the answer to part A, the change in momentum. You could also give the direction on that. In my diagram, it would be to the left. I'm not as concerned about that right now. But in part B, all right, if the change in momentum is 86 units, then the impulse is the same, 86 kilograms meters per second, because impulse is equal to the change in momentum. I'll write that down again. J equals delta P. That's a principle that's true. Impulse changes the momentum. Applying a force to an object changes its momentum in short time periods like this when you have large forces. Part C, the average force on a ball. So now we're just going to plug into the impulse equation. J equals F average times T. So we know our impulse here is 86 in our standard units. We're looking for the average force applied to the ball in 6 milliseconds, which is 0.006 seconds. Move the decimal 3 places to get that number. So the average force, it's a very large force applied to that ball for a short period of time, comes out to be 14,000 newtons of force that changes that momentum of that ball in that short period of time. Generally speaking, in impulse problems, there's large forces for short periods of time. Lastly, I'd like to review one more thing here. In the answer to part B, the impulse was 86 kilograms meters per second. We could have used different units there. Impulse, in this case, the J, we could have said it's 86 Newton seconds. That's equivalent to a kilogram meter per second. You didn't need to do that here. I usually stick with the standard kilograms meters per second. But a Newton second, as shown previously, is the same unit as a kilogram meter per second.